Ladies and gentlemen, thank you for watching this video. My name is Adria Mallol-Ragolta from the University of Augsburg in Germany, and today I will present our paper entitled An Investigation of Cross-Cultural Semi-Supervised Learning for Continuous Affective Recognition. The research question that we try to answer in this work is the following. Can semi-supervised learning approaches be used to automatically annotate multicultural affective datasets? For this, we focus on the automatic recognition of arousal and balance from acoustic and facial information respectively. Before going any further, let me introduce my co-authors, Dr. Nicholas Cummins and Professor Björn Schuller. My talk today is organized as follows. I will start introducing the topic and the dataset used in this work. I will then describe the methodology followed and present the experimental results obtained. I will finalize my talk with some conclusions. So let's start with the introduction. Social media platforms can be used to collect affective datasets. In order to train affect recognition models using supervised learning techniques, we need these datasets to be fully annotated. However, the process of annotating data is expensive and time-consuming. From the psychological literature, we know that different cultures convey emotions in different ways. Therefore, in order to annotate affect-related datasets, we need multiple annotators to determine the gold standard of a single sample, and we also need these annotators to share the same cultural background as the participants in order to avoid potential cultural biases. In this work, we focus on the recognition of arousal from acoustic information and balance from facial information in an attempt to assess the suitability of using semi-supervised learning approaches to simplify the process of annotating affect-related datasets. One important aspect of these approaches is that the quality of the annotations should not be damaged. Specifically, we aim to investigate the limitations of semi-supervised learning in cross-cultural settings. For this, we compare the performance of culture-specific affect recognition models trained using manual or cross-cultural automatic annotations. The data that we used in this work was released for the Cross-Cultural Emotion Sub-Challenge task of ABEC 2019. This dataset contains spontaneous in the wild interaction between pairs of German, Hungarian, and Chinese friends or relatives discussing about the conversion they have just seen. Let me play some examples here for you. Let's start with the German interaction.
Burger King Burger an. Oder so ein Burger. Ich habe das Ende aus wie so eine Werbung von Burger King oder McDonald's oder sowas.
Wie meinst du das jetzt schon?
Ich dachte erst, dann kommt jetzt gleich eine McDonald's-Werbung.
Let's continue with the Hungarian interaction.
Van egy ilyen idő, ameddig lehet beszélni.
Igen, gondolom, hogy addig lehet.
Jaj. Na jó, én most elmondom gyorsan magam, nekem kb. Az utolsó volt a legnormálisabb, mármint olyan szempontból, hogy legérthetőbb,
And let's finalize with a sample of the Chinese interaction.
广告我觉得很一般，因为广告觉得它就是阐述了一大堆的事例，它可以用在什么事情上，但是它那个功能上面是重复的，它就没有必要重复那么多次。
太多不同的那个什么，就广告就你刚开始可能看第一个觉得 OK， 然后到后面就觉得就蛮无聊的。
对，有点太长了，节奏不够快。
对，太长了，它其实真的是10几秒、20秒。
These interactions were recorded using a computer-based platform, which means that the video files contain the facial information from one of the two interactants, but the audio files contain information from both. In order to overcome this issue, in this work, we focus only on the information corresponding to the main interactant. This dataset was labeled in terms of balance and arousal. On the right-hand side, you can see a summary of the data available. As you can see, German and Hungarian interactions were available in all training, development, and test partitions. However, Chinese interactions were reserved for the test partition. In terms of absolute numbers, we observe that there are 68 interactions on the training partition, 28 interactions on the development partition, and 104 interactions on the test partition. So let's now move to the methodology section. In order to investigate semi-supervised learning approaches, we need to include semi-supervised annotations as training material for our models. For this, we first split our training data into two disjoint subsets. The first subset, SM, contains half of the interactions with their manual annotations. The second subset, S sub A, contains the remaining interactions but without the annotations. In order to investigate the performance of these semi-supervised learning approaches in this context, we followed this three-steps procedure. First, we trained a manual model, which was trained using the interactions from subset SM. Then this model was used to annotate the interactions from subset SA. In the second step, we trained an automatic model, which was trained using only the interactions from subset SA and their corresponding semi-supervised annotations. In the last step, we train a manual plus automatic model, meaning that the interactions from both subsets SM and SA and their corresponding manual and semi-supervised annotations were used as training material. In order to investigate the impact of culture in semi-supervised learning approaches, we forced the interactions populating SM to be selected in terms of culture. Therefore, we have three different scenarios in our context. In the first scenario, only German interactions are available in subset SM. In the second scenario, only Hungarian interactions are available in subset SM. And in our final scenario, interactions from both German and Hungarian cultures are available in subset SM. So this is a diagram depicting the system that we implemented in this work. And in the next couple of slides, I will detail the different stages. So first of all, we needed to extract low-level features from our input modalities. From the audio modality, we extracted 23 low-level descriptors of the IGIMAPS feature set. This feature set was extracted using the open source toolkit OpenSmile. From the video modality, we opted for extracting the intensities of 17 facial action units extracted using OpenFace. The audio and video modalities were recorded using different sampling rates. These differences were also translated on the frequency of the low-level features. So we tried to summarize the features extracted by creating sliding windows of 4 seconds length with a hop size of 0.1 seconds, and then we computed the mean and standard deviation for each feature dimension inside this time span. In this work, we model the current annotations in terms of the present and past input features, acoustic, both acoustic or visual features, and also we included past annotations as input features for our models. The neural network implemented in this work has two main components. The first one is a gated recurrent unit recurrent neural network, which is followed by 3 stacked fully connected layers. The GRU-RNN has 32 hidden units, and its aim is to learn a hidden representation of the input features, taking into account the time dependencies of the input data. Then this hidden representation is fed into 3 stacked fully connected layers with 32, 16, and 1 neurons respectively. The purpose of this architecture is to progressively compress the features extracted or the features learned using the GRU unit. Our model is trained using the concordance correlation coefficient as the loss. We use Adam as the optimizer, and we train our models with a maximum of 300 epochs. We also implemented an early stopping method in order to prevent our models from suffering overfitting. The last stage of our system is the post-processing part, in which we filter our annotations before assessing the performance of our models. So let's first focus on the experiments obtained for the arousal recognition from acoustic information. So in this table, you can see the concordance correlation coefficients obtained by comparing the ground truth and the predicted annotations when using half of the interactions available for training. So basically what we compare is in these 3 cultural scenarios, the performance of the manual and the automatic models. So as you can see, in most of the cases investigated in all these three cultural scenarios, the manual models achieve better results than the automatic models. In the next setup, in which we use all the available interactions for training, we compare two different types of models. The first one is a baseline model, which is trained using only the manual annotations. The second type of models are trained using both the manual and the semi-supervised annotations. Therefore, from these results, we can observe that in most of the cases, these hybrid models surpass the baseline model, and in those cases in which this statement is not true, the CCC is quite close to the baseline model. So now let's move to the balanced recognition from visual information. And again, let's start with the models trained with half of the training material in order to compare the performance of the manual and the automatic models. So here we can see that when only Hungarian interactions and when the combination of German and Hungarian interactions were selected to populate subset SM, so to train the manual models obtain higher CCC scores than the automatic models. However, in the first cultural scenario in which the German interactions were selected to populate SM, we observed that the automatic models outperform the manual models. Then, comparing the performance of our models trained using all the training material available, we observed that hybrid solutions also surpass the baseline in most of the scenarios assessed, and in those cases that this statement is not true, as happened before, the CCC scores are quite close to the baseline. So from these experiments and these results, we can draw the following conclusions. The first one, the culture of the interactions used for training the models impacted the overall system performance. From the comparison of the manual and automatic models, we observed that the best performances were obtained with the models trained using manual annotations. However, the models trained using semi-supervised learning annotations alone showed highly competitive results. Finally, from the comparison of the baseline and the manual and automatic models, we can conclude that hybrid solutions surpass the baseline models in most of the scenarios assessed. So here you have the full list of the references that I cited throughout my talk. And I would like to conclude my talk, with these couple take-home messages. The first one is that the performance of affect recognition models is cultural dependent, and that our results support the use of semi-supervised learning approaches to help easing the process of annotating affect-related datasets. Thank you all for your attention.